Now, I think we've talked a lot about how computers are building this model of the world and how they're starting to gain better understanding it. And our next panel is going to dive a lot deeper in how that actually crosses into embodied intelligence. So I'm really, really excited to introduce the moderator of that, Rocket Drew, who covers AI for the information. Rocket, are you ready? Are you on deck? All right, you can start heading up to the stage. And then after this, we just have another fireside chat and closing remarks, and that will be our program for the evening. It's been super informative for me. I hope it has been for y'all. We have mics for everybody here. Great. I'm going to hand this over to Drew. Drew. There we go. Great. Thanks, everybody.
All right. We're getting one more microphone over here.
I wondered why I had this.
All right, so my name's Rocket. I write about AI and robotics for The Information, which is a tech and business publication based in San Francisco. And the subject of this panel is world models, extending foundation models towards embodied intelligence. So that's fairly broad. We're going to talk quite a bit about world models, and then we'll probably talk even more broadly about foundation models, and we'll leave some time at the end for Q&A from the audience. But I'll get us started. Let's go down the line and do some introductions. Why don't you say who you are and also what your connection is to this topic? Like, what is your relationship to world models and foundation models?
I am Ashutosh Saxena, founder and CEO of TorqueAGI. In my background, I did my PhD from Stanford with Andrew Ng, was a professor at Cornell. So I've been designing loss functions and AI for robots for quite some time. After that, I have taken one company public called Catapult. So looking forward to the chat today.
Yeah, I'm Udaya. I'm the founder of IntuiCell, and we are kind of an odd bird within this panel because we don't come from AI. We come from a deep understanding about biological systems and how they learn in real world. So we are building network architectures from ground up based on first principles. We are not using reinforcement learning architectures. So we envision our agents to learn from the real world interactions. Yep.
Hi, this is Behrad Toghi. I'm the AI lead at General Motors. We work on a variety of problems within AI, but one of the highest priority problems that my team is focused on is building robots for manufacturing. And GM currently has 30,000 robots in its factories, so this is not a new problem. What we are trying to build is how much can we push this forward beyond just simple pick and place and repetitive tasks? How can we build an autonomous stack for robots? And I think that's also one of the hottest topics these days. So most of my background is also last 12, 13 years is a mixture of self-driving and manipulation.
That's great. So we have a really interesting variety of backgrounds on the panel. So hopefully that means we'll have some differing opinions about world models and the directions they should go. So maybe we should get on the shared page up front. What even is a world model? Like what are we talking about when we say world model? And I open that up to any of you. Hopefully we can get to some shared definition.
Yeah, so basically a world model means a model that has understanding about the physical world. So digital AI, like ChatGPT and other models, live in the online world. So think of words and thoughts. They have no limits. You can think about anything. But when you're trying to create a video game, a realistic video, or robotics, that is in physical world. And a world model implies that the model has the ability to reason about physics and the realistic nature of the problem it's dealing with.
Anything to add to that?
Yep. It also includes like having the internal representation of your own, like perception of the agent itself, like to understand the actions based on your sensory information.
Yeah, I think I do have the same question, that what's a world model, but I'll try to give my answer. I think the term world model has got a lot of traction and interest recently, as VLMs, VLAs, and foundation models have. But the idea of world model to me is just the transition probability of the world, which is nothing new in the reinforcement learning literature, in the Markov decision processes, and the classical decision-making literature. So to me is, if you're in a current state in the world and we make a change in the world, we take an action within this world, what's going to be the next state of the world? I think that's a good formalization of the world. Sometimes world models mean something beyond this, but to me, I think the formal definition of a world model is a probability distribution that defines what's the next state of the world given an action, which is nothing new. Again, people, Sudden and the whole reinforcement learning community has been working on this for many years.
And could that architecture kind of be model-free in the RL way you're thinking of it? Or would that still count as a world model potentially?
Yeah, I think what you're pointing out is there are two paradigms of learning and reinforcement learning. It's just model-free and model-based. But internally, a reinforcement learning agent or an intelligent agent in general is expected to have a model of the world. It can be learned separately and explicitly, or it can be learned as a part of the process. So I think that's what model-free or model-based points out to. But regardless of what's your learning paradigm and algorithm, if an intelligent agent wants to live in the world and take actions and interact with the world, it makes sense that they need to have an understanding of how the world works, which mathematically means what is the probability distribution of the future of the world, right?
Yeah. Just to add, I want to reinforce that a world model is really about when an agent, whether it's a video game character, a synthesized video, or a robot, is operating in the real world, right? So I think that's one of the common themes, and that's very important for physical AI.
Great. Well, I think the natural follow-up question for me is, do we have any of them today? Like, is there a model that you would point to and you say it qualifies as a world model? Do pure video models count, or is there something you're waiting to see before you think it has earned the title of world model?
Yeah, it's really hard to say. Like, it needs, from my perspective, it needs continuous learning and adaptation capabilities, which we don't have as of today. So that will draw it.
But that's something you're working on.
Yeah, that's something we are working on.
What's your approach to that problem?
So we are trying to learn based on the real world interaction. So we are trying to map the synergies between the sensory dynamics and the actuator dynamics as function, and the actuator dynamics, sorry. So we are trying to take the sensory information and convert them into motor actions. And that's where, so we are learning the models based on our physical interactions rather than pre-programmed data.
I think world models are crucial for robotics. For physical AI, we just heard from several talks today, data is a big problem, but I believe data is not the solution. Data will not help physical AI, and the reason is we need an incredible, intractable amount of data. Millions and $60 trillion will not solve the data problem alone. The solution, I believe, is world models. So many of the leading researchers, and at TorqueAGI, what we have realized is the agent or the model should build, either learn or bootstrap from certain known physics. In physical world, simple things like causality, gravity, known models of the world are easily available, and the model must know that so it can act in the world like what you said, and it can solve some of the very important problems. So at TorqueAGI, we are building such model. The world information is encoded in the model, and that gives it really high degree of training efficiency. So we have been working with several production clients and putting them to production in just about a couple of hundred data points.
That's great. That's really great.
I can add to that too.
Please.
I think the question was, do we have world models? And my answer is, of course we do. Newton's laws are world models, as I think you also pointed out. But the question is how complex and how much can we push? Basically, when we ask a world model, we should always ask the follow-up question that what's the space in which this world model is defined. If your space is pure kinematics, just X, Y, Z, of course we have very good world models. I mean, we have been launching satellites and such for many years. But if you want to push it all the way into visual fidelity, or very accurate physics interactions, or something that's actually, I think, has been the limiting factor and bottleneck in self-driving for many years is human interaction and all kinds of games that humans play together. This is a less of a problem in robotics, but it's a very major problem in self-driving. Understanding the social psychology and human behaviors, all the games that actors play in the game. That's a part of the world model. If you're driving on a highway, the other agents can be considered as a part of the world and therefore in the world model. But so the answer to do we have world models is of course. But then there are parts that these world models will become very, very complex and hard to model. And there are parts that there are closed form solutions for them, which you pointed out. We have many years of physics, and it probably is not a smart idea to throw all of that out.
So what exactly is the goal with these world models? What does it have to do with robotics? Like say tomorrow we got a world model that was much better than what we've seen so far. What would we do with it? What would it be useful for?
I think, let me answer that question a little bit differently. So when we exist in the LLM space, in the word space, there is a metric we use called cosine similarity. That was defined 20 years back, maybe 30 years back, and that forms the basis of loss function of the large LLMs, right? So going back to your problem, the known entity there in the word space is how similar my answer in the words is to what I wanted, right? And that is measured as a cosine similarity. That's a loss function. Great. Digital AI was worked with a large model. For me, the loss function in the case of robotics is measuring and being able to represent what do we want our robots to do in the real world. If you're working with a self-driving car and interacting with humans, the world model is the interaction cost, the cost of an accident, the cost of missing the lane. If you are trying to simulate a video or trying to model a robot, it's not just about injecting hard, brittle rules, but being able to represent that, oh, objects don't fly in the air. There is something called gravity. So if a model suddenly has 6 fingers, how many of people have seen those videos with 6 fingers and weird things happening? The key is the world model is built by telling the model, oh, you're making a mistake in the reality.
Are there other answers to this question? So you both imagined the world model providing kind of a training environment that you can get signal from the world model and then train against what the world model is saying? That's how you see it?
I think part of Steve's previous presentation, evals is a very operation heavy and super costly topic. A lot of robotics companies, a lot of self-driving companies have spent a lot of budget on running evals. So I think probably, I actually don't think the earliest gain we get from world models is in training. It's probably in something like regression testing and early eval results, then there's always the question, especially if you're in the industry, that how can I rely on this? You showed that a robot works, but how do I know if I take this into the factory, it'll still work? Or you showed me that a car drives on the street, how do I know if I deploy it on the road, it'll still do? But I think it serves as a great developer tool for regression testing and just performance tracking. And then regardless if you're doing imitation or reinforcement, the training will probably come a bit later. Or it can serve as a bootstrap for your training. I don't think where we are today, we can probably solve autonomy with a purely synthetic world model. At least that's, I think, my understanding of the world.
I think evals are certainly useful for testing the model or the performance of a system. I have a different view of how to use the world model, right? So it turns out when kids are born, it takes them almost 6 months to learn object permanence. Like something leaves and the parents leave and they come back, they don't realize that objects stay. They don't vanish in the air. It takes them about a year or year and a half when they start learning about gravity, that if they throw something, it's going to hit and something is going to break. So my view of world model is, when we are building a robot AI or a physical AI, how do we teach that model to internally start learning about physics, to give it the ability that it understands these basic notions, So next time when it faces a new problem, like you have 30,000 robots deployed in the factories, and you're like, oh, it's doing some gearbox movement, now I want it to do something else. It doesn't need millions of examples to solve that use case because it has learned that world model internally.
So do you or any of you see a role for the world model itself running on board the robot and helping with inference, sort of simulating rollouts of different actions, saying, oh, if I nudge the vase, it's going to fall, so I better not do that, sort of thing?
I think for me, the world model is the AI model that should be on the robot, in the AI, at the microsecond level, in the GPU. When the model is thinking, it should be thinking with the world model or the physics.
Well, also, I can answer, there's a lot of work on VLAs and robotics foundation models, but what's a VLA? It's a world model wrapped with an action head, essentially, right? And many other good stuff, but internally, it's understanding of the world again. If I take this action, what's going to happen to the world? Or what is its understanding of the scene that there's a bowl on top of a table, and this is the relative position of them. That comes from the world model. I think the main question is how large of a world model that you need to run on the edge. You don't need to understand everything in the world and the whole literature of English language and all the objects that exist in the world. Probably if you're deploying only on a manufacturing line that is doing one certain thing, or if your robot is a clothes folding robot. So I think the main question is what's the information content that the model needs to carry and how large that model needs to be on the edge, which again, this has a different answer from the on-robot and on-the-edge model and the eval model on the cloud and the training model. They probably have different sizes.
Yeah, like I agree with you, like understanding the physics of it and learning the interaction with the physical world allow you to generalize across different tasks because you're learning the basic interactions with the real world. So change in context, you can extrapolate to a new generalized mode of operation.
Let's talk about VLAs and foundation models a little bit more broadly for a moment. I suppose, Behrad, starting with you, you're looking at this kind of manufacturing context for automobile manufacturing. Where do you land on the sort of end-to-end approach in general? Do you see that as sort of the way forward for robotic AI, or are you still more partial to kind of a more classical or traditional approach?
I think there's not a solution that does all. I also don't think humans learn with a single learning paradigm, whether if it's imitation or reinforcement. It's probably a mixture of both. Also, we have built a lot of good stuff that flies plane and launches satellites and stuff, the whole model predictive control and stuff. So I think there's a lot of value and intellectual curiosity in doing a purely end-to-end pixels or sensor readings to control signals that we need to pursue that. But a real product is probably going to be a mixture of all these, like a system 1, system 2 kind of thing, which a large quote-unquote world model or a VLM or something like a JPA architecture is running on a lower frequency, on a bigger compute, and that provides you an understanding of your static world, and probably a lower reinforcement-based model runs at a higher frequency on a different compute that is providing you that high dexterity, the last touch. Also, the good thing, I've been thinking about this for a couple months, and it might be relevant to this topic, that as humans, if you ask me to make breakfast, the way I have learned how to make breakfast is by watching somebody and imitating them. Here's the sequence of actions that take. It's a very vision-heavy paradigm of learning. It's based on imitation. The subtask of picking up the egg and breaking it, I usually don't learn that through watching somebody, because hands often occlude that contact patch. It's also far from you. You can't really see to imitate it. You learn those kind of things rather through reinforcement and playing things and dropping things. And that's also very tactile and force-heavy learning rather than the first part, which was vision-heavy. So to answer your question, I don't think there's one solution fit all, that there will be one model that does all of it. I think we need a mixture of different learning paradigms and different sensor inputs.
So this is very interesting. I think when people think about VLAs and large models, the first thing that comes to mind is pixel to talks, right? Okay, I take what I have, rip it apart, I will replace it with the model. But that's not how even we do things. So let's think about a cup. When you think about a cup, I said cup, it's words, but it probably created a picture of a cup in your mind. It also gave you the 3D shape, and you also know that cup has a handle, you can hold it. So just the word cup goes and hits the same spot in your brain, which also stores the 3D shape and how to grab it. So that's what a model or a VLA is doing really, right? It's all actions, language, vision, planning is all in the same space. But that doesn't mean that at inference time, you have to go from pixels to torque. Once you have learned the knowledge about the cup and you are making breakfast, then you are actually doing system 1, system 2, sequence of actions. So what at TorqueAGI we believe in is a general model, but specialized agents that keep it interpretable. I think that's how humans do it. That's how, even if you are driving a car, you use a Google Maps system 1, right? And when you're driving, you forget about, and you're just driving the car, the system 2. So you can actually do both. Have a generalist model, but use it on the robot in a very interpretable and sequential manner.
Udaya, I think you have a particular view on this whole topic. I mean, what do you think everyone else is getting wrong about foundation models right now? Because you're going back to the drawing board and looking to biology for inspiration.
Yeah. We want the agents to learn from the real world interactions, like I was mentioning before, because we can never have enough data to let the agents work in real world. So we need them to learn, continuously learn for the changing real world dynamics. And we need them to learn the sensory dynamics and map them to the actuators within the agent. So that's the reason we are going back and we are building this whole sensory motor mapping from bottom up, based on first principles.
Do you have something on that?
I think one thing that I think we are doing a couple of things wrong. So I think one thing I always question is if on the simulation data, right? If AI is smart enough to create that data, why does it need that data back to learn? So that's my question to the panel.
That's I think you're absolutely right. A planner and then the engine behind the simulator are dual problems. Again, they're both solving, if I take this action, what's going to happen in the world. The one practical answer to that is you can run them on different compute. You can run a very, very large model for your simulator offline on cloud compute, but you necessarily can't run that same large model on the edge in real time. So one difference that mathematically I think they're dual, you're right. But practically I think they're differences.
Yeah, I guess is that a general argument against ever using synthetic data, say in the LLM context?
I think synthetic data is very useful for testing. I think what we have found is once the model has learned a lot of good knowledge, what it really matters. So I was talking to one of the senior vice presidents of Waymo. The real data that mattered to them costed them $500,000 because they kept on collecting data and they did not see any improvement. What really mattered was that unique intersection scenario where there was a pothole, there was an unprotected left turn, and that scenario, it's very hard to imagine in simulation. You have to see to know that it even exists. So I think when we are seeing and building models for robots from any problem, from humanoids trying to do household chores, it's really the problem is that data that, oh, I was grabbing this cup and such thing happened because it was that interesting bowl that someone had bought in a home. We don't have that just by thinking in simulation. It's the crucial high fidelity real life data points that really matter. So I think that's, and maybe we learn that by RL, maybe we learn that by other methods. I think that's what will really matter.
All right, great. I think we have time to take some questions from the audience. So I believe if you raise your hand or stand up, a microphone will magically appear. Or maybe I lied. No questions? Okay, I have some more questions, so it's fine with me. One question I have in general is about sort of how you're thinking about the analogy with LLMs. Like, to what extent are you tracking developments in LLMs and using those developments to sort of forecast what you expect to see in robotics? Maybe one particular question I have is whether you think generality is going to win out. Do you think the bitter lesson sort of applies to robotics as strongly as it does for language models?
I can go first on this. It's actually, timing is great because I had the pleasure of watching Richard Sutton again last week at NeurIPS, and it's always very amusing and enlightening to listen to him. So I do think, yeah, bitter lesson does apply for robotics, at least to me. The mapping from language to robotics is, I'm very pessimistic about it. I'm not convinced that the language is the right interface, because by design, language has two characteristics. One is that it's ambiguous, which is why we have poetry and language as a field of arts. Words can mean different things, and sometimes they can have different interpretations, which is not great for a structured task like robotics. And language is also lossy. It's a compression mechanism, right? Which is, again, not sometimes essentially the right compression mechanism for robotics. So I think a lot of lessons in terms of algorithms and such, we can learn all the infra work that goes into training LLMs, all of that immediately applies to robotics. But essentially building robotics technology on top of something that's built for language, I'm not convinced. And I think people like Jan LeCun that are working on JEPA type of models and such also believe in the same thing, that pixels or language are not the right representations, but rather an embedding a space that understand the world dynamics is better.
So I think it's interesting. I think once you start ripping apart the layers of an LLM, what you start finding is very soon the words representation go to a knowledge representation. And when we were building our own physics-inspired VLA model, what happens is we thought you are giving it a 3D model and training it from that data, but that same knowledge was getting embedded into a space and it's learning about actions. So I was giving the cup example. A 3D cup is the same as a word cup, which is the same as how you pick it up. So I think what happened in the language is 10, 15 years back, we had task-specific AI. One model was doing spam classification, something else was doing reviewing. All that was taken over by one generalist AI that you can now build agents and use it in different ways. I am a strong believer in robotics. In a few years, and it's already happening, we will have a set of AIs built by different companies. It will be a generalist AI, and then we will be fine-tuning or maybe using RL, maybe using data, and building many applications. So such an exciting times that the time to development for these new robots will be shortened to weeks rather than years, I think.
I like ending on kind of a prediction. It's the end of the year, so I'm kind of in prediction mode, thinking about what we'll see in 2026. Are there any other predictions you want to throw out there for what we might see in terms of world models or foundation models next year? And that'll be sort of where we end.
I had this chat with a colleague yesterday, so this might be relevant, that I think most of the robotics startups today are going very heavy on breadth in terms of task space. And the hope for that is if you go very wide on breadth, whenever you decide to go in depth in one vertical and becoming very good in that, one vertical, that's going to pay off because you've seen so many things, you've covered a large part of the task space. My prediction is this is going to change. Probably people are going to be less excited/obsessed with generalist agents and are going to see more value in agents that do one thing really, really well. I think we have to ship cruise control before we ship autonomy. My prediction is the term generalist or ChatGPT moment of robotics will probably lose a little bit of its attraction.
Yeah, I would agree with that. Like, we will move more towards a task-specific robotic agents rather than a generalist agent.
I think I kind of agree with both of you, but I want to differentiate between generalist model and a specialized agents or specialized robots. You can do both. What we will see is very, very powerful models that can do everything. But when we are building robotic applications or companies, we will see very, very specific, narrow, verticalized agents or robots that is still use some distilled version of the large agent. So my prediction is we'll see more and more models, whether they are JEPA, whether they are meta models, whether they are this and that. At the same time, the robotics companies that will succeed using those models will be the ones that choose a narrow application.
All right, an interesting lesson to end on there at the Humanoids Summit. So everyone, please join me in giving a round of applause to our panelists. Thank you.
Thanks, everyone. Oh, thank you, sir.